And so now using our definitions of sine, cos and tan in the unit circle is going to allow us to establish what the shapes of these functions look like when we graph them. So when we graph the angle against the value of sine theta, or when we graph the angle theta against the value of cos theta, etc., what that graph is going to look like. So let's first think about the graph of y equals sine theta. And to do that, we need to recall our definition of sine theta, and remembering that sine is all to do with the y coordinate of the point on the unit circle. And so we see how sine changes as theta changes. And so using this idea, or this definition of sine, we're now going to look at actually creating the sine curve. So as the angle gets larger, sine gets larger, then smaller again back down to 0, down negative to -1, and back up to 0. And in one rotation of the unit circle, we see this relationship occurring between the value of theta and the value of sine theta. And so what we note now is that if I were to lap the circle again and go from an angle of 2 pi around to 4 pi, I would see exactly the same thing occurring. Similarly, 4 pi to 6 pi, 6 pi to 8 pi, etc. We're going to see exact same repetition of this part of the graph that we've drawn here occurring. Similarly, if I had gone in a clockwise direction from the positive x-axis and gone from an angle of 0 radians around to -2 pi radians, I would also have seen this shape obviously occurring in the reverse direction. And so knowing this basic part of the sine graph allows me to then establish the entire sine graph, which is going to go on and on and on forever. And we just need to take that 0 to 2 pi section of the graph and essentially rubber stamp it and repeat it on and on and on. And we have the graph of y equals sine x. So you'll note that I've changed from talking about sine theta to sine x here. And all that is that we're going to change how we label our horizontal axis. Rather than label it as theta, we're going to shift now to the more common labeling of the horizontal axis, which is x. So this is the graph of y equals sine x. So a couple of things about this function. We've already talked about the fact that we only need to know about a small part of it to be able to then generate the whole graph. And that idea is to do with the fact that this is a periodic function, so it repeats itself, and it has a period of 2 pi. That's the span that we need to look at in order to see one complete cycle of the graph, and then we can simply repeat it. So it's periodic with a period of 2 pi. We also know that this is an oscillating function, so it moves the same distance above and below 0 and then repeats that. It oscillates around the x-axis, or around y equals 0. And the distance, the furthest distance that it oscillates away from that x-axis is what we call the amplitude of this oscillating function. So the graph of y equals sine x has an amplitude of 1. It oscillates to 1 unit above the x-axis, 1 unit below the x-axis, 1 unit above the x-axis, etc. And so we have the graph of y equals sine x. Now let's think about cos x and our definition of cos in the unit circle, remembering that it's all to do with the x coordinate of the point on the unit circle, and watching that green line we see how the value of cos changes as theta changes. And now if we use that definition to create our graph, we see that cos starts out at 1, decreases down to 0, out to -1, increases back to 0, and then back out to 1. And again we have the same situation with the sine curve. We could lap around again and see this exact same pattern occur again. We could have gone in a clockwise direction from the positive x-axis and looked at the part of the graph to the left of the y-axis. And so we generate this cos function. Again, it's periodic. We only need to look at a span of 2 pi units to see the entire shape, and we could then repeat that again and again and again. So it's periodic with a period of 2 pi. It's also an oscillating function, and it also oscillates only 1 unit above and 1 unit below. So it has what we call amplitude of 1. You'll notice that the graph of y equals cos x is very, very similar to the graph of y equals sine x. In fact, it's exactly the same shape. There's just a translation involved here. So all we would need to do is take this graph and translate it to the right, or to the right by pi on 2, and we would have the graph of y equals sine x. If we translated it to the left by pi on 2, it would be negative sine x. And so both graphically and in the unit circle, there's a whole lot of symmetry going on between sine and cos and a whole lot of relationships between those. And we'll look further at that a little later on. Lastly, let's have a look at the graph of y equals tan x. And tan x is a little different to sine and cos x. And let's just go back to our definition of tan in the unit circle, remembering it's all to do with the y coordinate of the point on that tangent. So it gets larger and larger and larger, and then gets negative and back to 0. The other thing that you'll note about tangent that was quite different from sine and cos, I'm going to play that again, is that in one lap of the unit circle, so from 0 to 2 pi, we essentially see the same thing happen twice. So we've seen that happen, and then it's repeated again, up, and then negative, and then back up to 0 again. So the same things occurred twice. And we'll see that in the graph when we plot out the graph from 0 to 2 pi, so it increases, 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 doesn't exist. Negative, 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 back to 0, increases, 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 doesn't exist, negative, 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 back to 0. So we saw the same thing occur twice. And obviously those points where the graph, the value of tan doesn't exist at all, will have asymptotes. So we've seen this whole thing occur twice in one lap of the unit circle. And what that essentially means is actually we didn't need to do one entire lap of the unit circle to see the whole definition of the tan curve. We actually only need to go from 0 to pi, and once I've seen what happens from 0 to pi, then I can just repeat that. So the tan graph is also a periodic function, but it only has a period of pi. We only need to see a span of pi in order to then be able to generate the whole graph. And similarly, we could have kept going around the circle, we could have gone in a negative direction around the circle, and we can generate this infinite function, y equals tan x, that goes on and on and on. X can approach infinity and negative infinity. So whilst it is a periodic graph with a period only of pi, we note that this time it is not an oscillating function. So the tan graph doesn't have amplitude, there isn't a maximum and a minimum, the graph doesn't oscillate the same distance above the x-axis as it does below. So tan doesn't have amplitude. So they're the graphs of sine x, cos x, and tan x.